is Dr. Anita Fleming. Anita is an emerging agricultural scientist who until recently worked at New Zealand's Lincoln University. Her expertise is in ruminant nutrition, agricultural system design, and connections between pastures, livestock, and consumers. Her team's research into metabolic signatures in beef cattle and humans is providing evidence of a connection between grazing management and consumer metabolism. Ooh. Anita also runs a successful dairy business in mid-Canterbury with her husband, where she applies practical thinking to merge on-farm experience with cutting-edge innovative science. Anita's going to talk for 30 to 40 minutes, and then we have 10 minutes for questions. We do want to record the questions as well, so you can either come up and ask your question, or we can repeat your question for you. Can't wait for this. Anita.
All right, hello everyone. Thanks so much for being here today, and thanks for having me. It's really cool to be over here in Tasmania. It's our first time here, so was delighted to be invited to have an opportunity to come and have a look around. So a little bit about me. You heard my bio, but I guess I up until recently I've been an agricultural scientist with Lincoln University, and so at the moment my husband and I have sort of decided to pivot a little bit my career. So today I'm going to be telling you about my experiences and the things that I've been up to the last 4 years, and recognising that now we're looking at, well, what next, and how do we make the most value out of the things that I've learned or have been learning. I guess I started my agricultural background, or started when growing up in the Hawke's Bay, up in the North Island over in New Zealand, in a little town called Wairoa, which has recently been really hit pretty badly with some cyclones and heaps of rainfall. So it's really hard done by little community at the moment. Really high like hill country, sheep beef predominantly, and a lot of forestry, and increasing amounts of forestry going in actually, which is also really challenging for the little community. And I started thinking, like, I grew up on a sheep and beef farm up there, and really enjoyed agriculture, but recognised that Wairoa was just a really small town. So, had to think, what am I going to do with myself? I have to get out of this little place to grow. And initially I wanted to go into and do veterinary science, but I felt, not quite that smart. So try my hand at ag science instead, and found myself down in Canterbury Plains in the South Island of New Zealand. Very different country to Tasmania, so very flat landscapes, really been grown in terms of intensive dairy farming down there, with incorporation of irrigation and that sort of thing. So I guess I started dairy farming by relief milking in the weekends and before classes and things to pay the bills while I was at uni. And after a couple of years, I actually met my husband, or my now husband, and who also happens to be a dairy farmer. So we pretty quickly ended up in our own sort of dairy business. So we started out share milking, 50-50 share milking. Does anyone here do dairy farming or anything like that? No? Yeah, used to? Yeah, cool. So 50-50 share milking is New Zealand. We have opportunities for herd ownership. So essentially the farm share milkers will provide the cows, they own the animals and run the business, and they get 50% of the milk check with the farm owner, who provides the land and infrastructure and all of that sort of stuff. And so we did that with James's parents for about James being my husband, who's in the corner there with my daughter Harper. So we did that for about 5 years, and really, really enjoyed it. Sort of at the same time, I finished up my studies with Lincoln. We started utilising a crop called fodder beet. Does anyone know what fodder beet is? Yeah, a couple. So essentially, fodder beet is like a big beetroot, is one way of describing it. It's very closely related to the beetroot family. But it's white and it's really high in sugar, so it's about 60% of the biomass is sugar. And in New Zealand, we started using a lot of fodder beet, so particularly in Canterbury and flat areas. And for our winter crops, it was really good for getting really high yield crops for feeding dairy cows during winter when they're not milking. But the challenge from a ruminant nutrition perspective is that it's a lot of sugar, not a lot of protein, not a lot of calcium, phosphorus. So it's not exactly a balanced diet, and it's kind of like letting your cows loose in a lolly shop and saying, here you go. So we started seeing on our farm a few challenges with things called like rumen acidosis. So that is when the rumen pH starts to drop down below a level that the microbes that live there can thrive, and in severe cases it actually leads to stock death. So yeah, we started having a few issues with a couple of cows dying. We noticed sort of every year we'd just get a couple, and we were working on terms of like transition management. So the idea being in New Zealand that you slowly transition cows up to a diet of, which is pretty much what we call ad libitum fodder beet, so up to sort of 10 to 12 kilograms of dry matter per cow per day, and a couple of kilos of straw for fibre. And the idea is that you do that over 21 days, so they get, it's about 1 kilo dry matter added to their diet every other day, so really, really fast transition period. And the key to getting good body condition score responses over winter. So in New Zealand, we like to carve our cows at a body condition score of about sort of 4.5 to 5, which means they need to put on 1 condition score during the sort of 6 to 8 week winter period that we have. So sugar is a good way of doing that because it's really high energy, but like I say, it's deficient in a lot of other things. So yeah, the other unique thing about fodder beet in New Zealand is that we graze it behind a fence. So fodder beet's been used for a long time in Europe, but not necessarily grazed as a crop. And so that means that there's additional challenges in terms of managing that crop. So for example, if cows break through a fence, they can get out, and like I said before, it's like letting them loose in a candy shop. They'll just eat as much as they can, and they don't have they haven't adapted the right mechanisms in the rumen to stop eating, so they'll just overindulge and then end up with acidosis. So really high risk situation. So having good transition and transitioning up to that ad libitum amount was kind of key to making sure that if they did break out, that they could sort of cope with potentially eating a lot of fodder beet. But like I said, it's not a balanced diet, so there's always this juggle between, mitigating animal stock risk and acidosis risk with also, making sure that they're actually getting adequate protein and calcium and phosphorus. And so we started to see an increase in metabolic illnesses post-calving. So particularly this thing called sleepy sickness, which is due to a lack of phosphorus. And like in New Zealand, we have limited infrastructure, so feeding cows on an individual basis on crop over winter is really challenging. So it's not as simple as just putting a bin in the paddock somewhere for a couple of the cows to have most of that, while those that are more submissive sort of get left out. So I started having all these questions about what is this doing to our business. Like I said, it wasn't like we were having a lot of acidosis issues that I could tell, but just noticing, because we were also grazing it in autumn and then feeding out any leftover crop to cows in spring, so across the shoulder of the season to supplement the pasture growth curve. And yeah, just started questioning, why aren't we seeing more of a milk response to this crop? Because it is high sugar, it should be relatively high energy, similar metabolizable energy content as grain or other, those sort of high starch inputs. And yeah, I guess that led me on my journey with Lincoln to continue research. So I got offered a position to come back as a tutor and part-time PhD student with Grant Edwards, who's now the VC there, and sort of delve into that question, why don't we see so much of a milk response with fodder beet? And at that time it was a really topical issue. So I started that research in 2016, and I did about 4 or 5 different experiments looking at different transitioning methods with cows, predominantly during lactation, so focusing on when cows are milking, because for us that seemed to be the biggest risk areas. So that's in autumn when cows are transitioning onto crop, but also in spring when they're calving, and so they can't be fed fodder beet during while they're calving, so they have to sort of transition off and then transition on again, and then you've got multiple mobs and cows constantly coming into that transition mob. So really complex sort of situation for us anyway. And so the research that I did there sort of showed, well, there wasn't actually much milk response. It was providing hard evidence that we weren't seeing a milk response. And a second experiment that I did the following year sort of revealed that actually up to 60% of cows experience subacute ruminal acidosis when they're eating fodder beet, when they transition to it. So it was actually, the problem was much bigger than we initially thought it was. The problem with acidosis and subacute ruminal acidosis is that it's subacute. You can't actually visually see it. So what's happening in the rumen, it's quite subtle, and that has made the problem, seem not as big a deal. But the challenge with low pH is that it actually burns the epithelium of the rumen, so the lining of the rumen, which is necessary for absorbing volatile fatty acids. So volatile fatty acids provide 70% of the energy for ruminant metabolism. So microbes in the rumen break things down, that provides volatile fatty acids, and those get absorbed by the ruminant for their energy, or 70% of their energy. So if they don't have the capability to absorb those acids, then they build up, which means pH spirals down. We see more lactobacilli, or microbes responsible for producing lactic acid. And lactic acid is far more stronger as an acid than other volatile fatty acids. So that's where the spiral starts, and where we start to see clinical acidosis. So that was one of the things that I found. The definition of clinical acidosis is that increase in lactic acid, and so we're not necessarily seeing that in cows that are transitioning to fodder beet, but 60% of them, regardless of using the best feeding cows on an individual level, making sure that they're allocated, if they're not eating their full allocations of fodder beet, that they're getting they're getting what they can eat, as opposed to just like a blanket herd allocation. All of those things, we're still seeing quite dramatic variations across the herd, and in terms of their risk for acidosis. And so really interesting stuff. Another one of the conclusions from that research showed actually that cows change their rumination behaviour in response to rumen pH. So they will actually ruminate more in the initial levels of subacute ruminal acidosis to mitigate the fact that they've got this build-up of acid. So saliva and rumination, saliva that gets circulated through chewing and mastication actually helps to increase pH in the rumen. And so that's a mechanism that they can actually use. So it's quite a dynamic variable, which, it's really, really interesting with all the cow wearables and things like that you see coming out now, and more of that information being, closer to hand. I think that's a really cool area to delve into. Yeah, and so, like I said, we found 60% of cows were experiencing poor rumen conditions despite best level practices. And actually that was something that information that we used in our own dairy business to change our systems. So we actually moved away from using fodder beet entirely. And decisions around that were also based on just issues with, it's an expensive crop, it's in the ground for a really long period of time, which means there's opportunity cost of having it on the milking platform because that's not growing pasture, which is actually the more efficient feed to dairy cows, or to graze to dairy cows. So we changed to a kale-based wintering system, and actually found that was better for our, not only like the farm owner and us as share milkers, found that actually worked for both parties because it was a lower cost, shorter crop, less animal health risks. We're finding it was observational, but we found that soil degradation was less, because with fodder beet, it's a big bulb that sits in the ground, and when the cows pull that out, then it leaves a hole. So we're seeing a lot less erosion and that sort of thing, which I think was, a positive outcome. But still had some questions about, how good are our wintering systems? Like, even with kale, cows are still stocked in a really intensive way over winter. We're still getting soil erosion. So it sort of wasn't, the answer to all of our problems, but just a step in it in, the right direction. And so that's when I started thinking about, what other plants can we use in our pasture-based systems. And so I was working with Pablo Gregorini at Lincoln University, who's the professor of livestock production there, and talking to a few of his friends, which I'm thankful to have as sort of mentors to me, which is Fred Provenza and Ian Gordon, Juan Villalba, working in the space of looking at what else is in plants that we don't really know about. And so when we think about ruminant nutrition, we think about the primary components of plant species, so carbohydrates, protein, lipids, cellulose, hemicellulose, all of those things. But we don't think about plant secret metabolites. And so, delved into this area of research, which was looking at what plant secret metabolites can offer. And at the time, plantain or ecotane, a particular cultivar of plantain, was becoming really popular in New Zealand for mitigating nitrate leaching because it's a diuretic. So it essentially increases the frequency of urination events in dairy cows. And that means that in a urine patch, we're not getting as much nitrate sitting in the soil and volatilising and leaching through the profile, which is a big problem that we have in Canterbury, actually, on our very stony soils. And probably you've heard some of the figures around our freshwater challenges. So it's a useful tool, but that was found a little bit by chance, in that somebody found the right cultivar and happened to test it. And so that sort of got me questioning, if I think there's about 68,000 known secondary metabolites that we know about. So it's a really challenging field to narrow down, particularly from a science perspective, to identify the right bioactive component in a plant and actually manage to capture that change in a grazing experiment. And that's one of the challenges that we've had in that field, of actually providing hard evidence that these offer different additional benefits. And so plant secondary metabolites are referred to as secondary because they were previously considered secondary to plant metabolism. So they don't, before some of the more recent research that's come out, it was sort of thought that they don't actually provide any great value to the plant survival, although we know that that's not actually the case. They provide lots of really important benefits for ensuring plants' persistence in response to pathogens or changes in the environment. So we tend to see them increase in at times when drought or environmental stresses, overgrazing and that sort of thing. And actually, in terms of about 20 years ago, or 10 to 20 years ago, it was sort of thought that they're anti-nutritional, so quite bad for ruminants. But we've actually been using plant secondary metabolites for human medicine for a really, really long period of time, back before the ancient Egyptians. So they offer some really interesting roles and really diverse roles that are not just about ensuring plant survival, but humans have been using them for antibacterial agents, antioxidants, anti-inflammatories, anti-carcinogenic. The list is like really, really long. Heart healthy. It goes on. And so I started doing some research in that space, and I did a bit of a meta-analysis, and I think the first search that I performed identified over 1 million articles, peer-reviewed articles that were published on the benefits of different bioactives and the impacts on human health. And so I thought that was really interesting. And then I started looking, well, what's that sort of research or that database in ruminants? And much narrower field. I think I came back with sort of under 10,000 articles total published on this space. And it is quite interesting because a lot of those compounds, so I'm talking about things like phenolics, phenolic acids, terpenoids, flavonoids, which are a phenolic compound, saponins and glucosinolates. And I'm sorry for the biochemistry speak. I will keep it to a little bit of a minimum, but if there's something that I've said that you don't understand, just swing out and let me know. And so started looking, at what the research was in terms of livestock, and found that a lot of those things actually sit in, found in the fibre of the plant, so cellulose and hemicellulose, and it's quite interesting because ruminants have a much better ability to break cellulose down, right? Whereas humans, we're not very good at it. So, there's actually a great opportunity to let livestock be able to actually break those things apart, partially metabolize them, and then, I was really interested, well, what's the pathway from there? Does it sit within, does it just get excreted out of the animal? Does it end up in the meat or the fat or the milk? And, what's the potential benefit for humans? So really started looking into that sort of like connection between paddock to human consumer. And so I was able to run a couple of experiments as a postdoc at Lincoln. And that was with a range of livestock species. So we looked at in deer and beef cattle, Angus cattle, and in dairy cows. So I ran a couple of experiments looking at the changes in milk composition. And we were actually also able to employ this technology called metabolomics, which is a really fancy word for looking at small metabolites. So basic metabolites that are involved in our everyday metabolism, things like glycolysis that allow us to create energy, but also looking at pathways associated with metabolism of lipids, with amino acids, all of those things. So untargeted metabolomics is the term, but it's just a really high level overview of all of the really small components within our everyday metabolism that we wouldn't normally think about from a scientific context, because there are thousands, so it's really hard to look at all of those at once, but thankfully technology's kind of evolved for us to be able to sort of narrow that down. And like I said, when you're looking at plant secondary metabolites, which are a really wide range of compounds, it's great to have a tool that will enable us to try and catch the simple changes on a metabolism level. And the idea being that hopefully we were able to use that process to connect metabolic pathways from the plant through to livestock and then actually the human consumer. And so then we started thinking, well, what plants can we graze? So in New Zealand, we traditionally graze perennial ryegrass and white clover. It's quite common mixture. And it's, as in terms of yield and all of that sort of seasonality of pasture growth, it's really great. But it doesn't provide a lot of diversity, and it doesn't provide a lot of plant secondary metabolite, complexity. And so we started the other common thing that we were doing on farm and across the industry. We started seeing a lot more cover crops and diverse mixes. So that was something we wanted to explore. If you provide diversity within a sward. But one of the challenges with plant species, like diverse swards, is that from a management perspective, they can be a bit challenging to keep control of, and that different plants have different sort of seasonality profiles. And so what we were finding within New Zealand is that, within a couple of grazing, a really complex pasture mix could dwindle down to a handful of 6 or 7 plant species really, really quickly. So we're sort of like thinking, well, how can we change that? How can we, get around that issue but still provide a bit of diversity for the livestock and the soil? And so we started thinking about this idea of functional diversity, and it's based on principles that have been developed from Fred Provenza and Juan Villalba over in the States. And really, it's actually around this concept that ruminants have this thing called nutritional wisdom. So they're able to, and it's something within our own team at Lincoln we've evaluated and got some evidence to support, but actually ruminants are able to identify within themselves what it is that they need to graze. So an example is like when they've got parasite burdens, that they can graze plants that contain, phenolic compounds and different bioactives that can actually help mitigate that naturally, and they will actually seek that out to mitigate that issue. One of the other things so we started sort of evaluating that and came up with this concept called functional diversity. So functional diversity is really about letting the animal decide what it is that they want to graze. When they graze a mixed sward, it can be really hard to make, particularly for a cattle beast, really hard to make really specific decisions about what to eat and when, because it's sort of within a feeding patch. They could have a range of things, and they actually might only want to eat chicory, as an example. But, there's only a couple of plants of chicory in front of them, so then they have to move off to another patch or another feeding station and, search for it. So it's quite diluted. Within functional diversity, what we've done is allocate discrete areas of the paddock containing a particular plant species. So within this initial research that we did, we looked at chicory, plantain, red clover, lucerne and perennial ryegrass, and so kept it quite simple. We're not doing anything too weird and wonderful. And so we grew them in adjacent swards across the paddock, so just strips essentially, and then that was strip grazed, so break fence put up so that at any one time cattle, deer or sheep or dairy cows had access to all 5 of those elements at once, and how they comprised their diet was actually down to their own nutritional wisdom, what they needed to do to meet their own physiological needs. And so really interesting outcomes from a livestock perspective, in that we found there was an advantage in terms of milk production, live weight gains for venison and for cattle as well. But it's really seasonal, so within the dairy studies, which were quite short term, we found there was about a 10% increase in milk production in those animals relative to the perennial ryegrass diets or a complex multi-species mixture. But actually, in when we looked at meat and live weight gain and venison and cattle, there wasn't as much of a difference, but it was really seasonal. So we didn't see a lot of differences in the shoulders of the summer season, but during the peak of summer, when things like chicory, lucerne and red clover are growing quite a bit more, and they're and during drought seasons too, because they've got quite deep tap roots. That was when we found some real good benefits with those species. And so we did that work, found some really interesting results, found that actually those animals were really efficient. From a milk production perspective, we started seeing this thing called incidental augmentation, or providing evidence for incidental augmentation. So that's a concept that reflects that when an animal doesn't have the ability to select and self-select what it is that they need for their physiological demands, they can inadvertently overindulge or underindulge in certain plant nutrients. a classic example that we see in our dairy systems in New Zealand is protein. So in perennial ryegrass and white clover swards, there's not a lot of choice, obviously, but those swards are quite high in protein for most of the season, and access to animal requirements. And what we found is when we introduced functional diversity, that actually the animals ate less protein. They chose to reduce the amount of legumes that they ate in their diet, and instead ate more things like plantain and chicory. And that diluted the amount of protein that they ate. So we saw reductions of sort of 20 to 30% of milk urea nitrogen across a couple of experiments. And similar responses in blood urea nitrogen, which is a proxy for nitrate in the urine. Really interesting stuff. And the next step was then, well, we've done this initial research. What about the metabolic stuff? So we finished the Angus cattle and the venison, and we took some milk samples from the dairy cow, and looked at the metabolic profiles, and found actually when we compared the metabolic profiles of animals that had ryegrass or a diverse, complex diverse mixed diet, they were actually quite similar. And I think that probably reflects the fact that when you've got a complex mixture, you've just got quite a dilution factor, so it's hard for an animal to eat a particular or lots of one particular plant species, for good or bad. But just that was an observation that we saw. When we gave them the functional diverse diet, we found a lot more differences, and a lot of the differences we actually don't know what they were. We weren't able to identify them. That is the challenge with untargeted metabolomics. We're not looking, like we had elements of things that we were looking for, but the differences in the untargeted were much greater in that a lot of the lipids and things that we found that were different, we just don't know what they are and what they do yet. So really interesting research in that. There's a lot more to explore in that area. And so the next step was, well, we finished these animals. We had a whole lot of ground up tenderloin, which I know is a bit of a travesty, but it was a good way of just homogenising the meat that we were looking at. And so we turned them into beef patties. And I'm just talking about the cattle stuff here. But and so we fed that to some people. So we got some willing participants that all came in a crossover design. So we had 24 people that came back every week for 3 weeks in a row and tried each one of our beef patties at 8 o'clock in the morning. So really, really hearty beef breakfast. And we looked at the metabolomic profiles in their plasma at 0, 3 and 5 hours postprandial, so after that meal, and found some really cool stuff. Like I said, a lot of the things that we did find, using an untargeted approach, we weren't able to identify exactly what a lot of the changes were. Some of the stuff that we did in a targeted method showed an increase in pantothenate, which is vitamin B5, in human plasma, and that was found as like a direct. There was a direct pathway from increases in the total diet that was fed to the cows in the functional diverse treatment, and that flowed directly through the animal through to the human consumer. And then the other one was vitamin E, and that's gamma tocopherol. So gamma tocopherol is one of 6 isomers of vitamin E. So the most common is alpha tocopherol, and really potent antioxidant, really good for heart health. It's an essential vitamin, which means we need to ingest it. We can't make it ourselves. And when we look at the nutrition of in processed foods and in future with synthetic meats and that sort of thing coming into our food systems, it's something that's going to be limiting in our diet. So if we can find ways to directly increase the amount of vitamin E, then it could be potentially really beneficial. It's also really good for cognitive and mental health. And there's been some research done showing that children that have greater levels of vitamin E actually have better cognitive development. And so, yeah, really, really cool research. This is, it's in the process of being published. It's in the final stages, which is why I'm comfortable talking to you about all of this. But yeah, we'll highlight that once it's published. It's something that hopefully you'll all be able to come and read and see for yourself. Yeah, like I said, just the way that this is run, it's really hard for me to go into all the details. And yeah, I don't want to bore you too much with the biochemistry and that sort of thing. So yeah, I guess for me now, it's just like I'm moving away a little bit from Lincoln University, and I'm doing that so that I can pursue more research. The challenge in New Zealand is actually we've got limited funding available. I think relative to Australia, New Zealand invests about 1% of the GDP into R&D, whereas I think over here it's sort of somewhere between 4 or 5%. And then you think about the scale of Australia relative to New Zealand in terms of our economies, is very limited funding, which makes all this stuff really, really hard to do. Metabolomics and clinical trials with humans are really, really expensive. And yeah, I have to thank Silver Fern Farms and John Barnes from Fertiliser New Zealand, as well as Lincoln University, for actually funding all this stuff, because these new novel ideas often don't get picked up by the sort of mainstream science and funding channels through CIROs and things like that. So yeah, no, really grateful for people that are willing to take a risk on something a bit new and different. Yeah, and so for me now, the next steps are looking at ways that I can actually implement this idea on farm. So been working in the integral health dairy farm, which I'll be telling you all about tomorrow. So you have to come along to hear more about the next step in terms of how does this actually integrate into a complete farm system. And yeah, so happy to take some questions, and yeah, hopefully you all enjoyed it.
Thank you. That was fantastic. Can't wait to read the paper. First question is from Matt. Are you happy to repeat questions?
Yeah, so the question was around if we did any work on soil health with functional diversity, and it's a great question. And that's not work that I've been directly involved in, but one of my colleagues, Sagara Kumara, Dr. Sagara Kumara over at Lincoln Uni, has been working the same paddocks that I was using to run the cattle work. He's done the same with sheep, and looking at linking soil microbial composition of that treatment compared with the other treatments, and also adding in an extra element of looking at a Agrosea product, which is a seaweed fertiliser company in New Zealand. And yeah, so we're saying that there are some really, really strong linkages, and I can't tell you specifically what, because it's still in the stages of being written up and reported on. But yeah, there are some really strong linkages, and actually, while we initially thought that having monocultures, because that's essentially what they are, would be bad for soil microbial diversity, what we're finding is that we're seeing more of the exorhizal fungi, which travel further afield, and probably the size of the strips that what we had, like they're not, in terms of the scale, we're talking about sort of 30-40 metre wide paddocks, so the strips are relatively narrow, and so thinking about that spatial component and what is the distance that those sorts of things can move, that's all stuff that we need to work out. But yeah, so really cool work there. How wide were the strips? So I think they varied depending on the paddock, but sort of about 10 metres, yeah, on average. Some were smaller, some were a bit bigger, yeah. Yeah, good question. Yeah, so the question was on with the functional diversity, whether it changed the rest periods and the grazing management, essentially, of that treatment. And the answer there is, in the component work that I did with the beef cattle, the venison, we kept them all the same as a controlled sort of experiment. In reality and practical, using practical knowledge, probably there does need to be some specific management applied to that treatment. From my own observation, what I found is in speaking quite practically, actually having them in discrete areas meant management was a lot easier, because at certain times of the year, like when, for example, chicory goes to seed and goes quite stalky, you've got the opportunity to be able to go in and top that if you need to stop it getting, because if it gets too woody and it gets grazed, then it becomes susceptible to disease and infection, and that's when we start to lose persistency. But yeah, in terms of the rest periods and grazing intensity and that sort of thing, that's also a bit of a challenge, because you do have selective grazing. Across all the livestock species, we found chicory is by far the most desirable. So they would, all animals would pretty much go straight to that area, graze it right down, and then sort of move on to the other components. Speaking quite generally, that's not to say that it's always the case. But yeah, so in terms of persistency and making sure that certain elements are not overgrazed, that's going to be a bit of a challenge, and it's something we've been working on within the Integral Health Dairy Farm to change, and actually finding some really cool stuff there about if animals actually do have a balanced diet, that they don't overgraze as much. So it's about tweaking how much of the diet is made up of chicory, plantain, red clover, ryegrass, and that sort of thing. And yeah, so there are some answers there. I will be giving more information about it tomorrow, so I don't want to give too much away today. But yeah. Does that answer your question?
When you talk about the animals eating less protein, as often they're in surplus, so it takes more energy to process that protein, which leads to a loss in milk production or weight gain. You said it dropped milk urea protein by 30% and also blood urea. Blood urea protein. Is that animal health issues, at those levels prior to the drop, or what's the issue with the milk protein urea?
Yeah, so the question was around the observation that functional diversity reduced milk urea and blood urea concentrations 20 to 30%, and whether that was an animal health issue or related to an animal health issue. And the answer there is, I think, probably yes. So like you say, ureagenesis, the breakdown of urea and cycling of it into the urine, does take up some energy. It's not a huge amount of energy. I think more than anything, though, it's just about enabling cattle or livestock, to graze certain components that actually do increase their efficiency from also a rumen digestion perspective. So thinking about rumen passage rate and that sort of thing. And when you're looking at perennial ryegrass, and at certain times of the year it's quite fibrous, compared to things like chicory and even plantain or red clover or lucerne, they've got more soluble carbohydrate content, which means that actually passage rate is a little bit higher. An interesting observation was that we didn't necessarily see increases in the amount of feed that they ate. So estimated dry matter intakes were similar, which sort of suggests actually the response is an increase just in efficiency. So just how they're processing that and how they're utilising those nutrients is actually just a bit greater. Yeah. Yeah. Yep. So I would like to see what the opportunities are to market something like that. If you could create a product that's high in vitamin E, then I think that that's something that could be really and in New Zealand we're unsubsidised, so anything we do has to be market led, and that's just the hard reality. So yeah, I think if we can provide examples that there is opportunity there, then other farmers will start to follow. And going back to your question, I'm sorry, I forgot what the next part of your question was?
It's about the different, you've identified three.
Yes, the types, yeah. And sorry, it went off on a bit of a tangent. It's what happens when you get a scientist talking about something they're really interested in. And so I've done some screening of what other plants are out there, and the opportunities are endless. Sagebrush is one example. And within the Integral Health Farm, we're looking at not just about forages, but also browsers too, because trees offer a range of bioactives as well. So it doesn't necessarily have to be just like our pasture species. Another example would be things like lupins, which have hydrolyzable tannins that could also be beneficial from an anti-methanogenic perspective. But it's just really about tweaking the system to make sure that we can provide livestock with things that they will actually willingly eat. Certainly my experience is if you have to force something to graze something, then it's probably not a good thing, just as a general observation. So it's a trial and error of working out what are the other things that are available that we can actually get commercially and as a seed and actually grow it and create something meaningful. So that will take time. The opportunities are endless. So yeah. Cool.
One more question? Can I thank Dr. Anita?
Thank you all.